Assalamu alaikum. My name is Irza Khan and my registration number is 23TE22. Today I'll be representing what DFS and BFS is with some examples. So let's start. BFS means breadth first search. Imagine dropping a stone in water and watching the ripples expand outward. BFS explores a graph in exactly that way. It visits all the nodes that are one step away, then all the nodes that are two steps away, and so on. Because it explores in order of distance, it naturally uses a queue that is first in, first out order. The first node you discover is the first node you explore fully, and DFS is depth first search. So, imagine exploring a maze. You pick a path and follow it until you hit a dead end, and only then do you backtrack to try a different path. That is a DFS. It prioritizes depth over breadth. It can be implemented with a stack, that is, last in, first out principle, or through recursion, where the call stack acts as the implicit stack. Over here, we have a simple example that is house search. So, this BFS strategy is that first we check every room on the first floor and then every room on the second floor. This is a systematic and thorough way you clear entire levels before moving deeper. This guarantees you'll find the key in the fewest number of steps if the key is on the first floor, but you might search many rooms before finding it. Now, the DFS strategy is that first you enter the first room, search everywhere, look under the rug, and go into the attached closet before moving to the next room. This is an intense, deep search of a single location. You might find the key immediately if it's in that first closet, or you might waste a huge amount of time searching a room thoroughly while the key is sitting on the table in the next room. Now, moving on to graph traversal. Um, yeah, it has three methods. First is discovery, second is expansion, and third is iteration. So, discovery. You start at a specific node, the root, and immediately mark it as visited so you don't process it again. Expansion. You look at the current node's neighbors. Any neighbor that hasn't been visited yet gets added to your processing container. That is a queue for BFS and a stack for DFS to be dealt with later. Third is iteration. You repeat this cycle, taking the next node from the container, visiting it, and adding its unvisited neighbors until the container is empty, meaning you've explored every reachable node. Now, there is a step by step traversal order. First, BFS order is A, B, C, D, E. Starting at A, the neighbors B, C are visited. Next, only after all neighbors at that level are visited does BFS move on to the neighbors of B, that is D, and then the neighbors of C, that is E. DFS order is A, B, D, C, E. Starting at A, it picks a neighbor that is B and goes deep. From B, it picks a neighbor D and goes deep. When D has no unvisited neighbors, it backtracks to B. Finding nothing new, backtracks to A and then explores the next neighbor C and finally goes deep from C to E. Now we move on to the example of robot pathfinding. This is a classic application in robotics and video games. The world is often represented as a grid. Each cell is a node, and moving up, down, left, or right, it creates edges. So, the BFS approach is because BFS explores level by level, that is, first all cells one step away, then two steps away, etc. The first time it reaches the exit, it has necessarily taken the shortest possible path. This is a superpower. DFS might stumble upon the exit quickly, or it might go on a long, winding journey away from the goal first. However, it is very sparse. In very sparse grids with fewer obstacles, DFS's stack can be more memory efficient than BFS's queue, which can grow very large. Moving on to the next slide, we have optimal routing. This slide basically reinforces the key takeaway from the previous one. BFS efficiency is that it explicitly states why BFS finds the shortest path. Its level by level exploration means that first time the goal is found, it's at the smallest possible distance from the start. DFS exploration is that it highlights the major flaw of DFS for this specific task. If the goal is in a shallow branch, but DFS first descends into a deep, distant branch, it will waste a huge amount of time before backtracking and finding the correct short path. Then moving on to the final slide, we have code demonstration. Firstly, BFS uses a queue, so the code is that first pop 0, it simulates removing from the front of the queue. It ensures nodes are processed in the order they were discovered, that is first in first out. And DFS stack has pop with nothing in the bracket. It removes the last element added, that is last in first out order. This forces the algorithm to go deep on the most recently discovered path. Notice how structurally similar the code is. The only difference is that data structures, that is queue versus stack, are different. On the last slide we have algorithm performance. It talks about time complexity and space complexity of both DFS and BFS. Now we'll move on to the code demonstration, code implementation of both BFS and DFS. Now, moving on to the codes, first we will see BFS implementation. This code implements a graph and performs a breadth first search BFS traversal. Here's what it does. It creates a graph first using a dictionary where each vertex maps to a list of its neighboring vertices. It adds edges. The add edge method connects the vertices. For example, adding edge 0, 1 means vertex 0 connects to vertex 1. Then it performs BFS starting from a given vertex. In this case, vertex is 2. It explores the graph level by level. First of all, it visits the starting vertex, then it visits its neighbors, it visits its neighbors, and so on. It uses a queue to track which vertices to visit next, and uses a visited set to avoid revisiting vertices. When it is run with the given example, as you can see, the result is 2031. Now we move on to DFS implementation. This code implements a graph with two different depth first search DFS traversal methods. First, it creates the same graph structure as BFS, for example, a dictionary mapping vertices to their neighbors. Then, first we do DFS using recursion. It uses function calls to dive deep into the graph. Then it starts at vertex 2, then it visits it, then recursively explores its first unvisited neighbor, continues going deeper into until reaching a dead end. Then it backtracks. Its output is, as you can see, 2013 over here. Then we move on to DFS using stack or iterative. It uses a stack, last in first out principle instead of recursion. Starts at vertex 2, pushes it onto the stack, then pops and visits vertices. When visiting a vertex, it pushes all its unvisited neighbors onto the stack. Its output, as you can see, is 2301. The order is different because the stack behavior is different from recursive. The key differences between BFS and DFS is that BFS explores level by level like ripples in water, and DFS explores by going as deep as possible along each path before backtracking, like exploring a maze by going down each path completely before trying another. Okay, so the output of DFS implementation can be seen over here. That's all for today. Thank you.